Okay, everyone. So now we're going to make use of the theory that we developed in the last section and use it to be able to solve linear, second order, non-homogeneous differential equations such as this. Okay, so what do? Well, using the theory that we developed last time, we first have to solve this one, which is pretty straightforward. Remember how we do it? We just get our characteristic equation. Lambda squared minus 3 lambda minus 4 is equal to 0. Factor that. Lambda minus Lambda minus 4, lambda plus 1 is equal to 0. And voila, we get that our solution to the homogeneous equation, I guess it's x rather than y now, is what? Alpha e to the, doesn't matter, negative 4, or positive 4 rather, positive 4t plus beta. And let me do it the same way it is in the book, just so that you got it. Yeah, plus beta e to the negative t. So there's the solution to the homogeneous. Now we need to find just any particular solution to this, okay? What's a function that when you take the second derivative of it, subtract 3 times the derivative of it, and then subtract 4 times the function, you're going to end up with 2 sine of t, okay? So this is hopefully something that when I explain it to you, you say, yeah, that makes sense. So let's think about it. What are functions whose derivatives and second derivatives and so on involve sine? Well, you know that's the sine and the cosine, right? The cosine, the derivative of the cosine is the negative sine, and the second derivative of the sine is the negative sine, and they're all kind of mixed in together there. So by the time you involve both the first derivative and the function and the second derivative, there's going to be sines and cosines more than likely that are involved in the answer. So here's what we do. We just start off with, and again, let me use the same notation I have before, if I have it. Yep, y sub p of t is equal to a times, which one did I choose first? The cosine of t, plus b times the sine of t. Okay? And then we just force it to fit this. So if this is x of t right here, then of course the derivative, x prime, is going to be what? Negative a sine of t plus b cosine of t. And then of course the second derivative is going to be negative a cosine of t minus b sine of t. Agreed? So there they all are. And so now we just plug it into this equation, and notice what we're going to get. I guess I have room enough to do it here. So here's the second derivative. It's going to be negative a cosine of t minus b sine of t. There's your second derivative, minus 3 times the first derivative, so that's going to be minus a sine of t plus b cosine of t. And then finally, minus 4 times the original function, a cosine of t plus b sine of t. Okay, getting kind of small there. Okay, so that's all it has to equal 2 sine of t. Agreed? So, how many cosines do I have over here? Let's collect them all together. I have negative a of them. And then here I'm going to have a negative 3b of them. And how many cosines do I have here? Negative 4a of them. So that's how many cosines I have over here. And notice I don't have any cosines over here, so that had better be equal to 0 by the time I'm done. And then the sines, I have negative b of them here, and what? Negative 3b of them here. let's see, sines. Positive 3a of them, okay? I didn't make that mistake on purpose, but I was just thinking, maybe as I was writing, that it's awfully easy to make mistakes here. This is where you just need to be very careful. It's just so easy to miss a negative or to do something wrong. So now I'm talking about the signs. So the signs is going to be negative b. Here it's going to be a positive 3a times sine. And then here it's going to be negative 4b again, right? Negative 4b. And that's got to be equal to, how many signs do I have over here? I have 2 of them. Okay? So now it's just obviously a simple algebra problem. Let's figure it out here. It's going to be negative 5a minus 3b is equal to 0. And then here it's going to be what? 3a minus 5b is equal to 2. Agreed? 3a minus 5b is equal to 2. So we need to get a one way or another, we need to eliminate one of those constants. And so let's get rid of the, well, let's see, how should we do it? Here, we already have different signs here, so let's multiply this thing by 3, and then this one by 5. So we're going to get negative 15a minus 9b is equal to 0, and I multiply that by 3, and now when I multiply this by 5, it's going to be positive 15a minus 25b is equal to 10. Agreed? Add them together, and you're going to get, what? Negative 34b is equal to 10. So b is equal to negative 5/17. Let's see if I'm lucky enough that I got the same thing before I did. Okay, and then there's your b. Stick it back into either of these equations, and you're going to get a, I won't do it, I'll just grab it, is equal to 3/17. There. So there's your particular solution. A is equal to 3/17, just for sake of space. Let me go ahead and put it up here. And beta is equal to negative 5/17. So there is a particular solution. And now we can use, from the theory that we developed in the last section, we know that the general solution of this differential equation, notice it's second degree, which means that it's going to have 2 linearly independent solutions as part of the general solution. And there they are right there. And so there they are. We'll put them there first. And then from the theorem that we had in the last section, theorem 6.2.3, all we do is we just add this thing on. So it's going to be plus 3/17 cosine of t minus 5/17 sine of t. There. So there's the general solution of that non-homogeneous differential equation. That's how it works. Let's try another one. Let's do the same thing, but now let's change this to 4t squared. Okay, so we still have the same homogeneous solution. We just need to come up with a particular solution for the non-homogeneous part, right? For this. So again, let's just think about it. Think about what you're doing. You've got a function, and you're taking its derivative, and you're taking its second derivative, and by the time you're done, you're going to want a 4t squared. So you know, what are you going to do? You could, if you let x be equal to 4t, or t squared rather, or negative t squared, this times t squared would give you this. The problem is, if this is t squared, negative t squared, so this gives you this, then you're going to have to take the derivative of that, and as soon as you get the derivative, you're going to get 8t. So you're going to have to somehow get rid of that 8t. And when you take the second derivative of this thing, you're going to get 8. So you're going to have to somehow get rid of the 8. So if you think about it, you're basically going to have to work with something of this form. Again, let me use the same notation I had before. Yeah, at squared plus bt plus c. And that way, you can figure out what A, B, and C are, so that by the time you're done mixing all those things together, you end up with just this, but the t term and the constant term go away. So let me get you started on this, and this is an exercise, so you can finish it. The answer is already in the book, but you need to go through the steps. And so what do? You say, okay, this thing, the derivative of it. Oops, I'm sorry. I should go back to x's again. Can't remember if I had y's or x's on the previous one. So this is the derivative is going to be what? 2at plus b. And then when you take the second derivative, you're just going to get 2a. And so now what do? You take this thing right here, then you take negative 3 times this, and then you take negative 4 times this, set it all equal to 4t squared, and well, let's just get you started on it anyway. So it's going to be 2a minus 3 times this, and then what? Minus 4 times this, and that all has to end up just giving you 4t squared. So now you look at the t squareds and you say, what's true of the t squareds? The t squared, you have negative 4a. Negative 4a, that's your, in fact, here's the way I like to do it. I like to just remind myself what it is I'm looking at. So I just put a t squared in a little box like that. I say, okay, I have negative 4a here, and that's got to be equal to 4. Well, that's easy enough. A is equal to negative 1. Okay, now let's look at the t's. If you look at the t's, how many t's do you have? Here you have negative 6a of them. And what do you have here? Negative 4b of them. And how many t's do you have over here? You have 0 of them. You already know that a is equal to negative 1, so you can put that in there and put this in here for a, and you can find your b, and then you can find your c, and you're all set. Okay, so that's the way that one works. Okay, let's try another one. Oh, and then what would you do? Then you would just take that particular solution and add it on to this one, of course. Okay, I've got the same thing again, but I've got 3e to the 2t. e to the 2t. Okay, so again, the homogeneous all stays the same. We just need to play with the particular. So you ask yourself the same question again. What function is it, function or functions, that when you take the first derivative and second derivative and so on, you get e to the 2t? Well, this one is easy, right? It's just e to the 2t gives you that. So that you don't even have to worry about a bunch of other things. Your particular solution, again, I want to put an x there, is going to be just some constant times e to the 2t. Because when I take the derivative of that, I get more of those, and when I take the second derivative, I get more of those again. And so so that's the way it goes. So let's just get started. The derivative is going to be what? 2a e to the 2t. The second derivative is going to be what? Bring the 2 down, it's going to be 4a e to the 2t. And now you stick this in, 3 times this, 4 times this, and you find out what a has to be in order to give you that. Okay? Very good. Okay? So then I ask, what's the answer? What's the general answer to this? And the nice thing is, again, and this comes from theorem 624, says that all we have to do is take the particular solution for this one, the particular solution for this one, and particular solution for that one, and you just add them all together. So here's your general solution right here, and then I forgot what they were already, but you take the particular solution you had for this thing, and then the one you had for this one, and the one you have for this one, and you just tack those all on together, and that's going to give you the general solution for this problem. So that's what's nice about linear differential equations. They work just the way you kind of want them to. Okay, very good. Let's try another one. If I can find it here. How about this one? Equals, instead of this, equals e, let's see, e to the negative t. Do I just have e to the negative t there? Yes, this is exercise 635 now. Okay? It's kind of nice. EX stands for both exercise and examples. So now we're working on exercises. But we have this one. So let's try this one. Same way as we did the other one, right? We're going to do what? We're going to try xp of t to be a e to the negative t. And so what do? We get the first derivative is going to be negative a e to the negative t. And then the second derivative is going to be what? The negative comes down, it's going to be positive again, right? E to the negative t. So you get that, and you stick it in here, and what does this say? It says the second derivative, so it's going to be a e to the negative t minus 3 times negative a e to the negative t, that's the first derivative, minus 4 times a e to the negative t, and that all has to equal e to the negative t. So let's see what we have over here. Let's see, how many e to the negative t's do I have here? I have a plus 3a minus 4a of them is equal to, how many do you have over here? You have 1. So what does a have to be? So notice here we're going to get 4a minus 4a is equal to 1. And say, uh-oh, we're in trouble. 0 is equal to 1. Wait a second. We wanted to find some number so that a would be equal to the right number, but it didn't work out. This thing annihilated is the word you sometimes use in differential equations. It all went to 0. I don't have anything left that I can set equal to 1. What's going on there? Why didn't it work? Do you see why it didn't work? I have something here which is part of the homogeneous solution. We already know from doing this part that when I stick e to the negative t in there, I'm going to get a 0 out, right? That's what it means to be a solution to the homogeneous solution. I know that if I stick in an e to the negative t, I get a 0 out. There's no way I can get this. Sure enough, we got a 0 out. See that? So so there's no way that this isn't going to work. Okay? On the other hand, this is a perfectly good differential equation. How do I go about finding the answer for it? Okay, what do I do? What do I do? Well, do you remember what we did a couple sections ago when we had a double root and we had a I forgot, but we had a e to the, I forgot what it was, negative. Let's see if I can find that one just to refer you back to it here. That's in section 6.1. Yeah, example 616. 616. That's where we had a double root. And so the way we got our second one was by taking the solution, one of the solutions, and putting a t in front. And so that's a reasonable thing to try here as well. Say, okay, we know that this thing right here is a solution to the homogeneous, so let's throw a t in front here and see if we can get a second solution that way, or get a solution that way. And that's what's going to work. I'm not going to go through all the details for you again because this is an exercise. But what do? Just have to carefully go through, take the derivative. Let's do it. Let's do that part anyway. Notice here you're going to have to use the product rule. The derivative of this is a times e to the negative t plus at. You leave this one alone, times the derivative of this is going to be e to the negative t times negative 1. So you're going to get that. And then you take the second derivative as well. And once you have both of those, then you can set it equal to this. And now you can ask what does a have to be so that your e to the t's add up to 1 and your t e to the t's add up to 0, because you don't have any t e to the t's there. So those have to add up to 0. Okay, so I think I gave you enough instruction there. So there you go. Okay, here's yet one more. What if we combine these two problems together? The problem of having a double root and the problem of it being a solution to the homogeneous. So let's try this one. X double prime plus 2x prime plus x is equal to e to the negative t. I think is what I want. Yes. Okay, let's do that one. So what do we do here? We start off by taking our characteristic equation and noticing that we do have a double root there. That's going to be s plus 1 quantity squared. And since we have a double root, we know that the homogeneous, I should have started with a y there because I keep wanting to put y. The homogeneous solution is going to be what? Let me write it in the same form I have it. It's going to be alpha e to the negative 1 negative t plus beta t e to the negative t. See that? So both of those things are solutions to the homogeneous again. They're solutions to the homogeneous solution when this is equal to 0. Okay, they're solutions to that. So now the problem is I've got this thing. What do I choose for a particular solution? X. And I can't choose this. This will give me 0. Can't choose this. This will give me 0. Oops. Let me make sure you're still with me here. Very good. Okay. I can't choose this. This will give me 0. I can't choose that. That will give me a 0 out when I stick it into this. So what do? Well, you just jump to the next highest power. So let's say capital A t squared e to the negative t. And so that's what you do. Okay, so you just go as high as you need to in order to not be part of the homogeneous solution. So it's kind of a simple idea. There are a lot of books of differential equations that just have all these rules. They don't really explain much. They just say, here's the thing to stick in there. And I'd rather try to explain a little bit. There are books that do a better explanation as well. I'm not the only one that explains. But the point is that if you understand the idea, then you don't have to remember a whole bunch of rules. You just think, oh, okay, you just need to go as far as you need to get away from the homogeneous and get something that's going to give you an answer here where you can find out your A. So I won't finish this off, but obviously you take the derivative, and here you're going to have to use the product rule again. 2at times e to the negative t plus at squared. The derivative of that is going to be negative e to the negative t. And then you take the second derivative and such, stick it all in there, set it equal to this, and find out what a has to be in order to satisfy it. So let me see. I think that'll work. Anything else I want to do here? No, that's it. Okay, very good. So that's section 6.3. In the next section now, we put all of this understanding of solutions together, and we really dig into the mass spring friction problem in more detail and really analyze that. So that's what's coming up. Very good.